explore the deep contradictions at the heart of scientific investigation and discovery. Research, the systematic pursuit of truth, contains deep paradoxes that challenge our understanding of knowledge. The first paradox reveals that deeper investigation leads to greater uncertainty. As we investigate deeper, each answer spawns multiple new questions, creating an expanding frontier of uncertainty. A single experiment might solve one mystery, but in doing so, it reveals 10 new puzzles we never knew existed. The depth of our investigation is directly proportional to the uncertainty we uncover. With basic tools, we see few details, but as our instruments improve, we detect more complexity and noise, not less. Heisenberg's uncertainty principle states that measuring position more precisely makes momentum less certain. This pattern repeats across every field. Sharper tools reveal deeper complexity, making certainty more elusive. The second paradox shows that observation itself changes what we observe. The observer effect demonstrates that the act of observation fundamentally alters the system being studied. Even with rigorous methods, researchers bring their cultural background and intellectual assumptions to their work. Even choosing what questions to study reflects subjective judgment shaped by culture and context. Pure objectivity becomes an impossible goal because perception and interpretation are inseparable from science. In psychology, participants change behavior when they know they're being studied, proving awareness itself disturbs equilibrium. The third paradox reveals how scientific systems suppress the creativity they depend on. Revolutionary ideas face rejection by peer review systems that demand evidence and conformity. To secure funding, proposals must sound feasible, which automatically filters out truly revolutionary concepts. History shows this pattern. Quantum mechanics, plate tectonics, and CRISPR all faced initial rejection for being too strange. The systems designed for reliability end up suppressing the very novelty science depends on. These paradoxes reveal that scientific progress operates through contradiction. Research advances through a cycle of doubting methods, questioning assumptions, and accepting uncertainty. True progress often requires walking directly into uncertainty rather than avoiding it. Research fundamentally means embracing contradiction as a path to deeper understanding. These paradoxes reveal the true nature of scientific inquiry. The certainty paradox shows that gaining knowledge actually reveals more uncertainty. The objectivity paradox proves that observation and interpretation are inseparable from research. The innovation paradox demonstrates that breakthrough discoveries often violate the very system supporting research. These three paradoxes form an interconnected web, each reinforcing the others in the pursuit of knowledge. Ultimately, genuine understanding begins precisely at the point where absolute certainty becomes impossible. Explore three fundamental paradoxes that challenge how we design and interpret research studies. Research design involves balancing competing goals, creating paradoxes where improving one aspect can worsen another. The first paradox involves the trade-off between tight control and real-world relevance. Laboratory controls like randomization and blinding strengthen causal claims, but these same controls can strip away the context needed for real-world application. Lab settings maximize internal validity with tight controls, while field settings maximize ecological validity with real-world complexity. Field studies add noise and interactions that labs suppress, often shrinking measured effects, but improving how well results transport to real settings. Lab effects are typically larger than field effects due to reduced noise and interference. This creates a fundamental paradox in research design. Designs that maximize truth in the sample can minimize truth in the wild, and vice versa. Consider a training app tested in different environments. A training app raises test scores 30% in a quiet lab, but has near zero impact in busy classrooms where real learning happens. The solution is to alternate between settings, use causal diagrams to identify truly necessary controls, and report treatment by context interactions. The second paradox involves the tension between discovery and confirmation. P-hacking and garden of forking paths arise when the same data are used to both generate and confirm a hypothesis. Genuine discovery requires open exploration, but using the same data for both exploration and confirmation inflates false positives. The paradox is that the exploratory behaviors that fuel scientific breakthroughs also inflate false positive rates. When exploration and confirmation use the same data, the false positive rate becomes inflated. The solution is to clearly separate exploratory and confirmatory phases. Use exploratory analyses on dataset 1 to generate hypotheses and analysis plans, then pre-register and test on fresh data or holdouts. For example, a researcher finds a surprising subgroup effect, pre-registers a replication focused on that subgroup, and confirms it in a new cohort. The third paradox is that measuring something can change what you are measuring. Repeated questionnaires can train respondents, sensors and cameras alter behavior, and task instructions become interventions by shifting goals. The act of measurement radiates out and perturbs the very phenomenon we are trying to observe. The paradox is that better measurement can worsen validity by perturbing what is measured. Consider a study that tracks sleep quality nightly. Sleep tracked nightly improves for the first week due to the Hawthorne effect, then degrades as anxiety about metrics grows. Solutions include unobtrusive baselining, randomized measurement schedules, and measuring reactivity explicitly as a moderator. All three paradoxes require thoughtful balancing rather than simple solutions. Each paradox represents a fundamental trade-off: internal versus ecological validity, exploration versus confirmation, and measurement precision versus reactivity. Pragmatic research alternates between settings and phases, uses theory to guide choices, and treats heterogeneity as informative rather than problematic. When effects reverse across contexts, that heterogeneity is itself a finding, not a failure of the research design. Explore three critical paradoxes that plague modern statistical practice and data science. Modern data science faces counterintuitive challenges, where more data or better models can actually lead us astray. First, let's explore how massive datasets can make us more certain about the wrong thing. With huge datasets, even trivial effects become statistically significant, but significance does not equal usefulness. When n is very large, even tiny meaningless effects can achieve p-values less than 0.001. This is the core paradox. Statistical significance tells us an effect exists, not whether it matters. Here we see a highly significant result with a p-value less than 0.001, but the actual effect size is only 0.02, which is practically meaningless. The solution is to focus on effect sizes and practical impact, not just p-values. Replace p-values with decision-relevant loss functions that measure actual business or scientific impact. Validate models using out-of-sample performance on real-world tasks, not just in-sample fit. Example: a churn model with AUC 0.71 sounds impressive but delivers negligible return on investment, but reframe it to optimize profit-weighted recall on the top 5% most actionable accounts, and suddenly it delivers high return on investment. The analogy: a microscope that can see dust motes perfectly, but misses the elephant in the room. Next, let's examine the tension between scientific progress and career incentives. Journals and funders prize novelty with rewards and recognition, while replications receive little credit despite being crucial for science. This creates a paradox. Researchers are penalized for doing the very studies that science needs most. Career incentives do not align with scientific progress, creating a fundamental tension. Example: a flashy lab result fades across 3 replication attempts, with effect sizes shrinking each time. But a meta-analysis can identify boundary conditions, like temperature, that rescue the mechanism in a constrained domain. Analogy: building a bridge. You celebrate a new design, but inspectors, the replications, are what keep it standing. Solutions require institutional reform to align incentives with good science. Registered reports have researchers pre-commit to methods before seeing results, reducing bias. Give credit for sharing datasets, code, and negative results, not just novel findings. Finally, let's examine the trade-off between prediction power and understanding. Flexible models like deep nets find complex patterns but are black boxes. Simple models expose mechanisms but miss interactions. The paradox: the best predictor is often the least explanatory. Complex models excel at prediction, capturing nonlinear structures and interactions, but they hide the underlying mechanisms. Simple models reveal mechanisms and policy levers clearly, but they miss complex patterns in the data. Hybrid approach. Use flexible learners to screen variables and structures, then fit interpretable models around identified regimes. Example: a black box ICU model flags important features. Then a sparse causal model uses just 4 variables to guide a protocol that reduces mortality. Analogy: a chef's palate, the black box, invents a dish. The recipe, interpretable, lets a kitchen reproduce it. Let's summarize the key lessons from these 3 paradoxes. With big data, focus on effect sizes and practical impact, not just statistical significance. Scientific progress requires institutional reform that values replication and negative results. For both prediction and understanding, combine complex models for discovery with simple models for explanation. Always validate your claims with rigorous out-of-sample tests on real-world tasks. Discover the paradoxes and challenges that make causal inference both fascinating and treacherous. Causal inference aims to uncover cause and effect relationships, but averaging, blinding, and ethics create surprising paradoxes. Let's explore how average treatment effects can completely hide what's really happening. A treatment can show 0 average effect, yet some patients benefit greatly while others are harmed. Here we see an average treatment effect of 0, but one subgroup benefits greatly while another is harmed. The average treatment effect is the sum of individual effects divided by sample size, which can equal 0 despite massive heterogeneity. Think of average effects like the average depth of a river. The average depth is 1 meter, safe to walk across, but you'll drown in the deep channel on the left, where it's 3 meters. How do we address this tyranny of the mean? Use stratified randomization to ensure balance across important subgroups like age, severity, or biomarkers. Report quantile treatment effects to show how the treatment works across the distribution, not just at the average. Pre-specify which moderators you'll examine to avoid data dredging and false discoveries. Let's look at a real-world example. A medication shows near 0 average effect, but quantile analysis reveals strong benefits for high inflammation patients and adverse effects for low inflammation patients. This heterogeneity analysis led to a biomarker-guided label, prescribing the drug only for high inflammation cases. Now let's examine the tension between blinding and realistic implementation. Blinding reduces expectancy and observer bias, but many interventions like therapy or education cannot be blinded without losing their essence. Perfect blinding can lead to poor fidelity, creating a new form of bias where the intervention no longer resembles real-world implementation. Imagine testing a parachute with perfect blinding. Testing a parachute against a backpack, placebo achieves perfect blinding but produces a meaningless result. The intervention is unrecognizable. How do we balance blinding with realism? Use objective endpoints like mortality, hospitalization, or test scores that are harder to bias. Have blinded adjudicators assess outcomes even if participants and providers cannot be blinded. Design active comparators that preserve contact time and expectancy while omitting the hypothesized mechanism. Consider a coaching intervention study. A sham coaching program with all active ingredients removed causes disengagement. A revised comparator preserves contact and expectancy but omits the key mechanism. Finally, let's examine the tension between ethics and causal identification. We cannot ethically randomize harmful exposures, like pollution, or withhold treatments known to work. Sometimes randomization and ethics are perpendicular, forcing us to find creative alternatives. The ethics constraint forces statistical creativity. Natural experiments exploit exogenous variation, like policy changes that affect some areas but not others. Regression discontinuity designs use sharp cutoffs, like test score thresholds, that create treatment assignment. Stepped wedge trials roll out treatment to all groups over time, satisfying ethics while preserving causal identification. Here's a real ethical design in action. A city has limited air purifiers for schools. They allocate by lottery, which is ethically fair, and creates random variation for causal identification of effects on asthma,